So in the pipeline of statistical learning, we know that there are maybe data preprocessing, the model training, and then the last thing that we have to know is the evaluation. Okay. Actually, before we go to the evaluation, we should know a little bit for the fact that there are two types of outputs. The one that give you like a point estimate, which is like a value, or maybe a single value, or maybe an entire picture, but everything that I said here only represents just an output. It's like a sample. Meanwhile, the interval estimates, which is the other type of the output, what you will get here sometimes is the range of your output. Sometimes are the samples. That means you get multiple outputs that lies within the range of your interval. So these are two types of the outputs. But most, I think all of the methods that we will learn in this course is going to be just the point estimate. So you can look at it as just a sample of your output. And after we know what is the types of output that we have, the next thing is what and where to measure. The first place that we usually measure is the predicting output. That is the output of our model versus the ground truth or the measurements, depends on what you have. The second thing is the learned coefficients, or maybe the learned parameters. If you remember, we have like X transpose beta, that was like our model, right? Sometimes we can also evaluate the model parameters beta. Sometimes. But usually for the model parameters beta, the way that we would evaluate it would be more on the sides of its general properties, such as, is this model parameters tend to be zero, like a non-zero coefficients or non-zero elements within it, more than how accurate it was with respect to its reference. Because sometimes it's very hard to find the reference for these, let's say, model parameters. Most of the time we don't know. But yes, for the output, we know. We have measurements, which is the noisy reference or the noiseless reference, like the ground truth. Okay, actually, in our course, we will generally separate the way that we would assess the point estimation into two types. The first one is the theoretical performance. The second one is the empirical performance, or sometimes we call it empirical results. It depends on what we are looking at. And in this course, I will focus more on the empirical evaluation, but the theoretical performance could be something that is quite important for you in the future. So let's say I will just cover the empirical first, and we'll go back to the theoretical. But in the slide, it will show theoretical first, so I'll just skip that one. Okay. Oh, by the way, before I go, all of these empirical evaluations are for regression task. That is our first task. Okay, if we have regression model, these are for evaluation matrices that we may be using it to judge the model performance. Okay, this is the theoretical performance. I'll skip it first. Okay, let's go to the empirical one. Okay, the first one is the residual sum square, but I think most of you would just see this formula and feel like this is a very common thing that we have. So basically, it is a sum of the error between your measurements, and your prediction result, and square, and that's it. It's very much similar to most of the sum of the errors that we calculate in a general case. Okay, can we move on? And by the way, just notice that here again we have this j from 1 to m, this signifying the number of samples. So when we perform evaluation, usually we will evaluate the difference between our prediction versus our reference on the testing sample. Unless we are doing this to find the model parameters, then it will be on the validation set. Okay. Next, another way to evaluate the performance is to use the residual standard error. The difference between residual standard error and the residual sum square, which is RSS, is the fact that you actually divide it by a quantity. So actually, this would look like something that we call mean square error in the empirical sense, except that we have P here. Actually, I'll put this way. The residual standard error can be computed in the same way that we normally compute the mean square error. That is, like j equal 1 to m, y hat j square here, and m. You can do this as well, but the reason that normally when people talk about this residual standard error and they will negate the p here is because usually if your model parameters is very large, let's say you're dealing with deep learning that have the number of parameters around 1 million, what that suggests is that you will need the number of training samples to around 1 million as well, in order to ensure that you will have a unique solution for your model parameters. So that means that actually, if you only divide it just like this with m, what's going to happen is that you are going to it's like you are dividing by something very large. So you are overly penalizing the error. Or on the other word, you will see a very small error. So you underestimate the performance of your model. So usually, if you divide it this way, they will say that you are underestimating the model performance. Because the result could be very low. The number could look very, very low. So that's the reason why they have to negate with P. And P here is the number of model parameters. Let's say if we go back to the example of linear model, where you have X transpose beta here. Beta is a vector, and if it's like a very long vector, you will need a very long m. So yes, if the beta has a size of, let's say 100 times 1, then whatever m you have to negate m with 100. Just like that, just so that you are reducing the effect of your denominator. And yes, for a very simple linear model where you have only, let's say, beta 0 and beta 1, or just beta here, your p is equal to 2. That's your number of parameters. This is just an example. And the reason that they have to have this denominator, even though it sounds like you don't want to have it because you keep reducing the impact, is still better than without it. That is, if you look at just the residual sum square, the problem with this type of evaluation is the fact that if the scale of y is very large, let's say you're dealing with a number of 1 million, this sum square could give you like a 1 million square, which is, 10 to the power 12. That's a lot. But for this one, at least you kind of, subtract it down by dividing by the number of samples. That means you are averaging them. But you also don't want to overly averaging them. That's the reason why you negate it by p. And sometimes we take the square root so that we ensure that whatever we look at are in the same scale as what you are looking. That is, let's say if the scale of y is around 1000, after you square it and then, after you take the square and then you take the square root, it should go back to the same unit. Another thing that may be better than this, this one, you still have to guess if whether or not the range of your RSE is making sense. But what if you can scale this number to just 0 and 1 and make sense of your performance? That becomes the motivation for using what we call R-squared statistics. This R-squared statistic could be seen as the accuracy for regression task, because this value will have the value between 0 and 1. And if you get the R square of 1, that means you are 100% accurate, because it is the 1 subtract by the error term, where the RSS is a residual sum square that you get from the previous slides. So it's actually this one. However, it is divided by the TSS. And TSS here is the total variance of the samples of the measurements y from its mean. So you just kind of like take the sample, I was going to say sample variance, but it's not totally sample variance, because you just sum square of this variance, and then you have RSS as a nominator and divided by TSS. Actually, if your model is a linear regression, you can ensure that RSS will always, actually the TSS minus RSS will always be lower than TSS. We will provide that derivation in the linear regression, but usually R-squared statistics have this benefit of the fact that when the definition is between TSS minus RSS divided by TSS, usually the value will be between 0 and 1, so it's easy to interpret. Actually, that's it. Not yet? Okay, sorry. There's a few more. Next thing is the standard error. And this one could be a little tricky, because most people will refer to its theoretical definition, that is standard error is the empirical expectation of y hat that is zero shift from y bar, given that y bar is like the average of y hat. So pretty much it's measuring the deviation of the prediction value, because this is a prediction value and this is the mean of the prediction value. But usually people will take it empirically, which is this formulation. That is, you maybe maybe you do the sum of the square between these two terms and divide by m. That's it. Usually I'm not sure when we will be using this, but I remember that it's kind of, how should I say, the standard error sometimes can be tricky to compute, but in this laboratory we wouldn't go that deep, so you just need to know that, okay, empirical formulation for standard error is just this. Yeah, and we will skip quickly. Because, okay, maybe, just a little bit. If you want to compute this value, okay, simple saying is that you run your inference for m samples, let's say m being the number of samples in testing set, right? And then you negate it from the mean of that estimated, of that prediction, because this is like a average of that prediction, and you can compute it. That's it. What is tricky about this is that sometimes they will evaluate the standard error with some types of estimator that is also use like a bunch of data to compute. That is in the slides of the standard error of the sample mean. But I think I will not go into this. This is more like an example of what it would look like. If you actually have to draw, let's say, y-hat from a bunch of samples, and then after you have, not y-hat, I'm sorry. If you have to draw a prediction from a bunch of samples, and then you have to produce that bunch of predictions. So this is what's happening in these slides. But don't worry, it's just an example.